So, hi everyone. Hi, Wish. How you doing? So, welcome to this new episode of DevOps Insight. Today, we are very happy to welcome Wish Shi, and we'll talk about TiKV. Is that how you pronounce it? TiKV. Okay, sorry. Okay, so I will let you do your presentation, and then we will take questions from the audience. Wait. Oh, can you wait a second? I think there is a sound problem. Can you try to talk, please? Can you say something? No. Just 1 second. Yeah. Okay, can you try to talk?
Hello, everyone.
Okay, it's working. Sorry about that. Okay, let's go. Let's do this.
Thanks again for inviting me here to have this talk. First, I would like to introduce a little bit for me. I'm Wish, and I'm an infrastructure engineer from PingCAP. I have been working for improving the TiKV's performance and its ecosystem usability for several years. So this talk is mainly targeted at people who are not familiar with TiKV or even haven't heard about it. So I will focus on introducing its ideas and designs. And there won't be a lot of technical details. So there will be 3 major parts in this talk. I will begin from what is TiKV, and then move on to how it works. And finally, I will talk about what's new in the TiKV version 4.0. Okay, so let's begin. What is TiKV? TiKV is a key value database, and it is open source, distributed, and supports transactions. And actually, its design is inspired from Google Spanner and HBase, but the design is simpler and more practical. For example, it is easy to be deployed on a standard cloud environment, and you don't need any special file systems. TiKV is currently a CNCF incubating project, and it's up for graduation. And with the great support from the community and users, TiKV has more than 7,000 GitHub stars now, and there are more than 200 contributors. And TiKV is currently adopted by more than 1,000 production users. And you can see in this picture, TiKV has production adopters across multiple industries. So now seeing so many users adopted TiKV, you might be curious about why they choose it. I will introduce its key features, so you can have an image about what you can do with it. So as the name indicates, TiKV is a key value store, which means it provides key value oriented interface like get, put, delete, and scan. And there are some high-level infrastructures built upon TiKV, for example, TiDB. It is a distributed relational database. Actually, TiDB is the reason that TiKV was originally created. There are also some other attempts, for example, Redis. It is built by the community, provides Redis protocol. It is backed by TiKV so that it has the same advantages as TiKV. TiKV is cloud native, so it simply means you can easily deploy it into any environment. For example, physical machines, virtual machines, or containers, or clouds, and so on. TiKV offers scalability. This is one of the key features TiKV provides. For example, if you want to store more data, or if you want to serve more payloads, you can just deploy more TiKV nodes. Data and requests will be rebalanced automatically. And besides scalability, another key feature is high availability. It is achieved by supporting geo-replication. The data you stored in TiKV have multiple replicas like this. For a 3-replica cluster, the service will not be affected if one replica is down, and the service will maintain strong consistency. And I will talk a little about strong consistency later. And these replicas can be scheduled to different physical locations. So the cluster can suffer from, for example, machine failures or even data center failures. It all depends on the location level you set. And the fantastic thing is that no matter you want to scale out the performance or to provide more data redundancy, the scale out operation is online. So it simply means you don't need to shut down the whole cluster and your service will not be affected. And of course, the scale in operation is also online. Both scale out, scale in are online. TiKV is transactional. It provides externally consistent distributed transactions with strong consistency. So there are two parts I just mentioned, transaction and consistency. For transaction, it can be pretty useful when you want to operate with multiple key value pairs. And you want them to happen all at once or none at once. And about the strong consistency, it roughly means, for example, suppose there are 3 replicas. And after you write a value to one replica, that value is ensured to be read out from the other 2 replicas. So this is strong consistency. Now let's dive deeper to see the internal design behind these features I just mentioned. This is the overall architecture of a single TiKV node. And as you can see, it runs just like a normal application. Clients connect to the nodes by using the gRPC protocol. The fundamental part is a local storage engine. This storage engine is not distributed. It does not have any knowledge about replicas or shards. And upon that storage engine, there is a consensus model. It handles replication with strong consistency. So now we have an engine and a replication layer above it. With both, we have now a distributed storage engine. And finally, there is a transaction model. This transaction model implements MVCC and distributed transactions. MVCC stands for multi-version concurrency control. And let's take a deeper look one by one. First is storage engine. TiKV does not build a new storage engine. It uses RocksDB instead. RocksDB is a local key value store developed by Facebook. It is actually based on Google's LevelDB. And the reason TiKV uses RuxDB is very simple. RuxDB is mature and battle tested. It is high performance and has all features TiKV wants. So there is no need to build another one. And now let's see how TiKV provides fault tolerance. So suppose there is only one node, one replica, like what you see here. When this node is down, data cannot be accessed anymore. Your service will become unavailable. So how to prevent from this scenario? A simple solution could be using a synchronous replication. For example, all writes to the leader node are copied to the follower node asynchronously. And when the leader is down, we can read data from the follower. However, there is a problem. It is not strong consistent. Let us see. For example, in this case, C equals to 3 is successfully written to the cluster when the leader is up, but then it cannot be read out again from the cluster again if the leader is down, because the follower doesn't have this log. So the strong consistency is broken. And how about using synchronous replication? So in synchronous replication, the write to the leader is finished only after it is successfully replicated to the follower. And there are new problems. Suppose there is a network partition like this. Network partitions here means, for example, the leader cannot connect to the follower, and the follower cannot connect to the leader. But for example, there is a client, and the client can connect to both. So when there are network partitions, the leader cannot finish the write, since it cannot replicate these write operations to the follower. So finally, the cluster does not work anymore. It cannot serve any requests. So in the synchronous replication, strong consistency is maintained, but it is not available when there are network partitions. And the solution in TiKV is to use a consensus algorithm called Rust. And actually, there are other consensus algorithms. If you are interested, I will recommend a course from MIT. It is 6.825. So if you have interest, if you have interest, you can take a look at that course and you will learn more. I will explain a little bit about the Raft algorithm. So in the Raft consensus algorithm, there is one leader and there are followers. There is only one leader. The rest are followers. And the client reads and writes to the leader node. It does not communicate with the follower node. And the leader node replicates operations to the follower node. And the client request will be succeeded if the majority nodes have persisted the operations. For example, in this case, we have 3 nodes. And as long as a leader node and one of the follower, for example, in this case, the second follower node, as long as they have both received and persisted the operation, the request is succeeded and is finished. And then when it comes to a node failure, for example, the current leader is down. The up-to-date follower, this one, becomes the new leader, and it serves requests from the client. During this process, the client can read latest data from time to time, even if the leader is changed. And what you need to remember is that the whole cluster is available as long as the majority nodes live. So this is how TiKV provides high availability. And in this case, we have 3 nodes. So the cluster is available and provides strong consistency when 2 or more nodes are live. Now we know how high availability is achieved, and let's take a look about the sharding design. The sharding provides horizontal scalability. TiKV uses range sharding, so it's the right side. Range sharding means adjacent keys are put together as a shard. And in other systems, they may use hash sharding, so it's the left side. And the difference is that range sharding is more efficient to scan operations. If you remember, TiKV provides get, put, delete, and scan. So in range sharding, scan is more efficient. So TiKV uses range sharding. And now let's put replication and sharding together. In TiKV, each shard is called region. For each region, TiKV uses raft algorithm here to replicate its data across multiple TiKV nodes. Since data will be split into multiple shards, so actually there will be multiple raft groups. In this picture, there are 3 raft groups for each shard. The region 1 has a raft group, the region 2 has a raft group, and the region 3 has another raft group. Did you still remember the concept of raft leader and follower? So here, the raft leader is annotated with black border. And in this picture, node A has a raft leader, which is region 1, and node B has a raft leader, which is region 2. And for node C, it has a leader, region 3. And now, for example, if the client wants to read a key, let's suppose the client wants to read B, and you will find B is in the region 1, and the region 1's leader is node A. So finally, the B, no matter its read or write, will be processed by node A. And similarly, if you want to read or write key D, so D is in the region 2. So the region 2's leader is node B. So D will be processed by node B. Okay, now let's see how scale out works. Suppose we have added a new node here, new node D into the cluster, and the scheduler will balance 2 things. It will balance replicas, and it will also balance leaders. First, the scheduler will balance the replica. So a new replica is created in node D. And then the raft leader is balanced. In this case, previously the leader is in node A, and now it's transferred to node D. So now node D has a leader. And finally, the actual replica. As you can see, we have 4 replicas here, and actually we only want 3 replicas. So there is an actual replica, so it is removed. And now you can see node A stores less data. It only has data region 2 and region 3. And it also handles less requests because it has fewer leaders. Previously, it has a leader in region 1, but the leader is transferred, so it no longer needs to handle any requests in the range of region 1. And let's take a look at node D. So this newly added node handles some requests because it has the leader of region 1. And for this node, both storage and performance is scale out. So this is how scale out works. And finally, I want to explain about the transaction. And first, I want to explain why we need the distributed transaction. So the reason is that, for example, in this case, different paths, they may be involved with different TiKV nodes. It depends on the region leader. Let's see. For example, this transaction will modify A and modify key H. So for key A, it is in region 1, and for key H, it is in region 3. And maybe the leader of region 1 is node 1, but the leader of region 3 can be node 2 or node 3. It can also be node 1. Anyway, these leaders may not be the same. They will be handled by different TiKV nodes. So this is why we need distributed transaction. And for TiKV, TiKV use the percolator algorithm to perform the distributed transaction. I will not explain the detail of the percolator algorithm because there are many materials online, and I will only talk about its features. So this algorithm is basically a two-phase commit, and it provides snapshot isolation. Each transaction requires a timestamp. This timestamp is allocated by a central timestamp oracle. So this is how this algorithm works. And the timestamp oracle and previously I have mentioned the scheduler. They are both implemented in another component called the placement driver, or PD. And PD also serves a cache of the region information. So for example, TiKV clients can know which TiKV node to send according to the region information from PD. And PD is high available, so the whole system is high available. Typical TiKV cluster. So each TiKV node stores different data shards, and all shards have multiple replicas. And there is the clients. They use gRPC protocol to communicate with each TiKV node, and as well as the placement driver. Okay, recently TiKV has reached version 4.0. So I would like to briefly introduce some new features available in this version. The first one is follower read. As we talked before, each raft group is served by the raft leader. So clients send requests, no matter it's read or write, to the leader. And sometimes this may cause some problems. For example, the leader node may be very busy. So in 4.0, we introduced a new feature called follower read. It's just like its name. It means the clients can read from the follower. And this read will maintain the strong consistency feature. So when clients can read from the followers, the payload of the leader node is reduced, so it can handle more requests. The second one is an engine called Titan. So I previously said that TiKV used RocksDB as its storage engine. And Titan is not a new storage engine. It's a plugin of the RocksDB. We have some designs online, and if you are interested, you can take a look. And Titan is supposed to solve some problems about the write amplification of the RocksDB. and it can, let's say it can improve performance. And then there is a unified thread pool in 4.0. If you have used previous versions of TiKV, you will find that there are many different thread pools in TiKV. For example, there is a thread pool for the coprocessor, and there is a thread pool for writes, and there is also a thread pool for reads. And in 4.0, we have introduced a unified thread pool. So all these kind of requests, coprocessor, read or write, they can be processed in one thread pool, and they will have priorities. So, for example, large requests will not block small requests, and the overall threads number of threads is reduced. So this sometimes improve performance because small requests will not be blocked by large requests, and the users will be more easy to configure these thread pools because there is only one thread pool now. And there is a load balanceability. This means the region in TiKV will be split by the load. If you are interested in this feature, you can take a look at our website. And for the ecosystem, we have a new tool called backup and restore. So this tool is very high performance. It is distributed and supports, for example, snapshot isolation provided by TiKV. And meanwhile, it will maintain strong consistency. And it supports external storage, for example, S3 from Amazon or other kind of cloud services. It also supports incremental backup and also full backup. So this backup and restore tool is very powerful. We have also introduced some security improvements. For example, in 4.0, there is a transparent data encryption. The data stored on the disk will be encrypted transparently. And we also improve the TOS. For example, the backup and restore tool, it supports TOS, and TiKV or PD both supports TOS. And all of them supports the online renewal of the certificates. So your service will not be affected because if you renew a certificate, the cluster doesn't need to be restarted. Okay, so basically this is everything I want to introduce today, and the TiKV community is always working hard to improve its performance, stability, and reliability. So you can join the community if you want to make it better, or you just want to, for example, adopt it in your applications. Now there is a Go client and the Rust client. I would recommend the Go client. It is pretty much ready to use. To reach the community, you can just take a look at the GitHub page or our homepage or this community link. Okay, I think that's all for today, and I would like to answer questions if you have. Thank you.
Thanks, Wish. That's super interesting. So I have a few questions. What is the main use case for TiKV? Is it like a replacement for etcd and console, or do you know if people use it for other things?
Oh, so compared to etcd, the main difference is how large the data you store. For example, in the homepage of etcd, it suggests that you can store, for example, 1 gigabyte of data to the etcd, and TiKV is much larger. It is ready for gigabytes, and so this is just basically by design, because, for example, there is only one leader of etcd, and you can see for TiKV there are rebalance or membership change, or even data shards or multiple replicas. So TiKV is for storing much more serious data and as a building block to store this one.
Okay, so my question was, do you know what do people use it for? Is it so it's not for configuration? It's more for storing a lot of data. Is that what you're saying?
Yeah.
Okay. And so I know it's being used by TiDB. Could you tell us a bit about this? How it works with it? Does it implement like a MySQL engine for TiDB, or is that on the TiDB side? I guess.
Yeah. So TiDB, actually TiDB is MySQL compatible, but it's re-implemented. It's compatible for the protocol and for some user-defined functions. But it's based on TiKV, so it has advantages of TiKV. For example, it is distributed, and because its data is stored on TiKV, so it can be horizontally scaled as well.
Okay. You mentioned on the new feature project Titan about limitation to RocksDB. Could you tell us a bit about this?
Okay. I would like to expand a little bit more about the Titan engine. So RocksDB is a typical LSM tree. So in the LSM tree, both keys and values are stored in this tree. So if your value is very long, there may be problems because there are too much data in this tree. And if you write, for example, 1 kilobyte, and this 1 kilobyte value will be amplified multiple times. For example, it will be in the WAL or in the memory table, and then in multiple levels. So this is how write amplification comes from. And for the Titan engine, it is inspired from a paper called Whiskey. So they have similar ideas. For Titan engine, these large values will be extracted out of the LSM tree. So so these large values will not have these write applications. The overall performance will be improved.
Okay.
If you have interests, actually we have some materials on the website, and there is a link about this Titan engine, and you can click about it to learn some designs or how it works.
Okay. And so I know TiKV is written in Rust. I guess it was because it offers better low-level performance. And for example, I know CockroachDB is 100% in Go, but you think it offers you an advantage over them because Rust is faster for a low-level operation?
Yeah, TiKV is written in Rust, and we choose Rust for several reasons. Of course, the first reason is performance. So Rust, it is compared to Golang, it is very efficient. If you have read the source code of CockroachDB, and you will find that they recently rewrite some of the core models to use C or C++ instead of Golang. So they finally choose the compiled languages like C or C++ to improve performance. And for TiKV, since we use Rust, it is just as efficient as C or CPP. And besides that, we all know that Rust is a memory-safe language. So we will not face, for example, race conditions or dangling pointers.
Yeah.
Yeah, these features. It is pretty cool.
Yeah, I agree. And you mentioned that you recommend the Go client over the Rust client. Is it because the Go client is more mature, or is there a difference?
Yeah, the Go client is more mature because, for example, it has all features um, to run a typical application. And the Rust client is not very ready. For example, it has some missing features. One of the missing features is region cache. So without region cache, the performance may be not very good. And as far as I know, the Rust client is still in development. So currently, I would recommend to use the Go client.
Okay. Okay. Speaking of cache, can you use it TiKV like something like Redis, like a replacement?
Yeah, actually, actually, we have found a community project called Tedis, and I mentioned it before. So for Tedis, it's
Okay.
based on TiKV, and it
Nice.
provides
Yeah.
provide interface like Redis. And you may take a look at this project.
Do you support data sets like Redis or?
For the performance, of course, it will not as efficient as
Yeah.
the Redis, yeah, but it has scalability.
Okay. Well, thank you so much, Vish. Is there anything else you would like to add? No, can you hear me?
Yeah.
Okay, so thank you. We don't have any more questions. Is there anything else you would like to add before we leave?
No, everything is done here.
Okay. Well, thanks, Wish, and thanks everyone for watching, and see you soon, hopefully. Cheers. Bye
Thank
bye.
you. Bye.
Bye. Thanks.